Hi, welcome back everybody. Let's jump straight into it. In this lesson, we're going to be talking about gravity. Do you understand the weight of this situation? What is gravity? That's a great question. And honestly, the branches of physics that deal specifically with gravity get super crazy, like general relativity, space-time, black holes, absolute insanity. And I have some awesome online resources if you're interested in learning about those more profound aspects of gravity. But in this course, we're going to keep it simple and talk about the force of gravity as it has to do more with everyday physical concepts. And here's the basic principle. Every object with mass is gravitationally attracted to every other object with mass. Let's talk about mass. How would you define mass? Mass is a measure of the amount of stuff in an object. What's the stuff? Well, if you look real close, we have molecules, atoms, subatomic particles, and elementary particles within them. Each of these has a certain amount of mass. It's fundamental and universal. And what this mass really means, where it really comes from, is beyond the scope of this course. We're going to keep it simple. Basically, speaking objectively, in any given object, there is a certain amount of stuff that, if you look deep down, is made of a certain huge number of elementary particles that nobody can argue. This object is made of this amount of stuff. That is the mass of the object. Look at that object in any circumstance, and its mass is always the same. So, seriously, if two things have mass, they are gravitationally attracted to each other. Here's how we would represent that in a force diagram. Here's two objects with mass. They're attracted gravitationally, so the forces point toward each other. And these forces are a Newton's third law force pair, so they're equal in magnitude and opposite in direction. So if any two objects with mass are gravitationally attracted, why does it say this chair come flying over toward me due to our mutual influences? Well, the force of gravity is actually very weak and difficult to detect unless one or both of the objects is very massive, like a planet or a moon or a star. In fact, there's a mathematical formula that actually allows you to calculate the exact amount of gravitational force acting between any two objects, so long as you know their masses and the distance between them. The gist of the formula is basically that the more massive the objects, the greater the gravitational attraction between them. And the closer the objects are, the greater the gravitational attraction between them. In this course, we're not going to be concerned with the formula, but it's been around for hundreds of years, and it's been correctly used to predict the motions of extremely far away objects in the universe, as well as things here on Earth. So I can calculate the magnitude of the gravitational force between myself and Earth, and then I calculate the magnitude of the gravitational force between myself and that chair if it's sitting, say, a meter away from me. And that is only 0.00000000003% the strength. Yes, I really calculated that. So because the gravitational force between two objects of this sort of size is so insignificant, we just ignore it. For the purpose of this course, and really any introductory physics course, anytime we're analyzing force in an everyday situation, we only consider gravitational interactions between Earth and everyday objects, and not gravitational interactions between two everyday objects, since, as we've seen, it's basically zero as far as we're concerned. We'll talk more about mass soon. Let's briefly talk about the distance aspect of gravitational attraction. I mentioned that the closer two objects are, the more they're gravitationally attracted. The farther apart the two objects are, the less the gravitational attraction between them. So the force of gravity drops off as objects get farther apart. But it's important to think about just how rapidly does it drop off? Well, we have a pretty good sense of the gravitational force we humans experience down here on the surface of Earth. Now say that I go up to the top of a 100-foot tall building. Compared to when I was on the ground, how much do you think that the Earth's influence of gravity on me has changed? Really, it's changed by less than 0.001%. Okay, what if I'm on an airplane at cruising altitude, say 35,000 feet above the surface? Compared to when I was on the ground, how much do you think that the gravitational influence has changed now? The answer is still less than 0.4%, even at an altitude of 1,300,000 feet, which is the altitude at which the International Space Station orbits. The effect of gravity only decreases by 11%. The point is, Earth's gravitational force does decrease as we get farther from Earth, but it's not noticeable until we're really, really far above Earth. So, for all intents and purposes, we'll treat the influence of gravity due to Earth as constant if we're anywhere near the surface. So, what about weight? Is weight just another way to say mass? How would you define weight? How would I define weight? This. In our life here on Earth, the weight of an object is the fact that Earth's gravity is pulling that object toward Earth's center. I can feel the weight of a heavy object I'm holding because Earth is pulling that thing downward, and I'm exerting myself to oppose that force. I can feel the weight of my own body because I have to use my muscles to stand up. So long as I'm hanging out here around Earth, Earth is always pulling me directly toward its center. To me, here on Earth's surface, I might call that direction down. This is why, in order to be stable, we have to stand straight up. This is the struggle when babies learn to balance and develop their muscles so that they can stand up and walk without falling over. Because Earth is always pulling on them. It's a lot easier for us to simply lay down. So, I'm laying down. I'm not in motion. Is the force of Earth's gravity still acting on me? Do I still have weight? Well, I'm not moving. I'm not floating around the room. So long as I don't use the muscles in my body, I'm not going anywhere. Why? What's keeping me right here in this position? The force of Earth's gravity is literally keeping me pinned to the ground, and a big old scale underneath me would still read the same thing as if I was standing. We can see other evidence of my weight, like in the compression of the couch beneath me. And if the couch were somehow suddenly removed from beneath me, I'd be back in motion, heading down toward the Earth until something else caught me and held me up, like the floor. So yeah, Earth's gravity is always pulling me down toward Earth. It's always pulling. This doesn't mean that I'm always falling, but it is always pulling. It's just that a lot of the time I've got something else acting to push me away from Earth, and the forces balance. More on this later in the course. Here's another way to think about it. I've got a glass of water. It's not moving, just chilling on my desk. Is gravity acting on the water in my glass? Well, let me ask you this. Where in the glass is my water? It sounds trivial, but am I ever going to look over at my glass and see the water anywhere other than the parts that are closest to Earth? Will I ever see the water in my glass look like this, or just floating around randomly in there? No. The water is pinned to the bottommost parts of my glass because Earth's gravity is acting on every single atom that makes up the water, pulling all the water in the downward direction. If I turn the glass like this, where does the water go? And why? It's always being pulled down toward Earth's center. All things around us, literally all things with mass around us here on Earth, are being acted upon by the force of Earth's gravity all the time. Later in the course, we'll talk about the effects of gravity on the motions of objects. But, pop quiz, is gravity acting on you? Well, are you on or near Earth? Yeah? Is the force of Earth's gravity acting on your house? How about a manatee floating in the springs? Or a helium balloon that's floating upwards through the air? Well, let's think real quick about floaty things, like the balloon or the manatee. Does the air or water around those objects make it so that the force of Earth's gravity doesn't act on them? If those things are able to float upward, does that mean that gravity isn't pulling them downward? Is gravity canceled for that thing? Let's follow that path and see where it leads us. Think again about that balloon floating upwards. Lots of people would assert that gravity can't be acting on it, since it's clearly floating up and away. If gravity isn't acting on the balloon, one might say that the balloon is weightless. How could you reconcile this with the fact that the balloon is made of matter, and therefore has mass? Anyway, say that the balloon is rising, and suddenly a predatory bird flies up to the balloon and pops it with its beak. What's going to happen to the balloon once it's popped? It's going to fall back down to the ground, right? Because of gravity. So we think that Earth's gravity would act on it then. How is it possible for Earth's gravity to not act on the balloon at first, and then all of a sudden the balloon pops and gravity does start acting on it? How could the force of Earth's gravity get turned on and off like that? What would it take to make that interaction happen or not happen all of a sudden? How can Earth's gravity be pulling on some objects around it, but not others? Let's take a step back. Any force is caused by an interaction between two objects. We've seen that any two objects with mass are gravitationally attracted to each other. A balloon and the particles of helium inside of it are made of matter, right? So they have mass. Because of this, Earth and the balloon are always gravitationally attracted to each other. In order for Earth's gravity to stop acting on the balloon, we'd have to delete the Earth. This might seem technically correct, but you might be wondering still, how do we explain that something can float, even going up and away, if gravity is always acting on it? How can anything move upwards? I'll leave this as a brain teaser that will be solved in the next lesson. But for now, let's establish a quick little exercise in deductive reasoning that will help us determine whether an object is being acted upon by Earth's gravitational force. This will work like a syllogism. If you don't recognize the term syllogism, don't stress it. You've probably heard these before. Here's an example. All dogs are mammals. Zuzu is a dog. Therefore, based on these two truthful statements, one can conclude that Zuzu is a mammal. Here's another. If I am carrying an umbrella, that means that there's a chance of rain that day. Today, I am carrying an umbrella. Therefore, one can conclude that there is a chance of rain today. So, how can we apply this logic to help us do physics? Well, all you need to remember is that if an object is on or near Earth, then the force of Earth's gravity is acting on that object. Period. My glass of water is here near Earth. Therefore, I can conclude that the force of Earth's gravity is acting on my glass of water. Now, we can kind of cut loose and apply this to literally any object that's on or near Earth's surface. So, hopping off that really long tangent, what is weight? The weight of an object is the force of gravity acting on that object. Usually that means we're simply talking about Earth's gravity, since we're usually concerned with things here on Earth. The greater the mass of an object, the greater the gravitational attraction between it and Earth, and therefore the greater its weight. The farther an object gets away from Earth, the less the gravitational attraction between it and Earth, and thus the less its weight. But like I said earlier, you have to travel hundreds of miles above Earth's surface to experience an actually noticeable change in weight. You've probably heard how your weight would be different if you were to visit, say, the moon. The moon has a different size and mass than Earth, and so the force of gravity due to the moon, i.e. your weight on the moon, is different from what you would experience here on Earth. We won't really be concerned with this though, because in almost all cases, we're thinking about the force of gravity here on Earth due to the gravitational attraction between us and Earth. Unless, of course, we are thinking specifically about something that's happening, say, in deep space, which, although not directly applicable to our everyday lives, is really useful for learning about force and motion. Thinking about something out in space, far enough away from stars or planets that might have a gravitational effect on it, we can visualize a system that's isolated from outside influences, which in physics is sort of like a stripped back approach. Without the influence of things we experience here on Earth, like gravity, we can think about the motions of objects solely due to some other specified forces. Now, talking about gravity and forces outside the context of Earth might seem a little unnecessary at first, but as a burgeoning physicist, it's important to develop a more universal understanding of concepts like force. Weight is not an inherent property of any object ever. It arises due to an interaction, due to the fact that that object has mass and exists near something else with mass. Think about an asteroid, a big old chunk of rock that was formed billions of years ago. It's massive, quite literally, it has mass, it's made of stuff. But if it's out in deep space with nothing around it for vast distances, there's essentially no gravitational force acting on it. It does not have weight. But say that we can play God, like we're playing a simulation computer game, and somehow grab that asteroid and place it near the sun. The sun and asteroid will experience gravitational attraction. The asteroid has weight. The asteroid is getting pulled toward the sun. Say that we then grab the asteroid and place it near Earth now. The asteroid is going to be pulled near Earth due to Earth's gravity. It's not like the asteroid was made to be close to Earth naturally, and so that's the place it seeks, as if it's somehow been willed that way. It's pulled toward Earth solely because of a gravitational attraction. Same goes for literally every object around us right now. These objects just happen to exist on or near Earth's surface, like us. Theoretically, we could take something elsewhere, like to Mars. If we take an object to Mars and let go of it near the surface, it's going to fall down toward Mars. No longer will it fall toward Earth. Of course, this isn't practical, but it's philosophical and still important to think about. Earth isn't special in this regard. Tons of things exist far away from Earth. Those things can and do often experience gravity, just not Earth's gravity. But we have to remember that it's still valid. All of this is to say that when we, in our daily lives, see objects fall down, it's because that thing happens to be near Earth, like us, and basically everything else we interact with. It's not some divine order. It's not that thing's natural resting place in the universe. Those concepts are incompatible with physics. We have to remember that the scope of physics is, quite seriously, universal. And our life and interactions here on Earth is just one teeny fraction of all the things out there in existence. Things with mass that interact, gravitational forces between other star systems, planets, asteroids, galaxies, which exist by the billions. The actual same principles, like that formula I was talking about, apply there, just as they do here. It's called the law of universal gravitation for a reason. We humans just happen to exist on one little planet right here. And since our entire lives take place here, every day we're immersed in a very specific scenario. But look elsewhere and we can use the same physics to understand what's going on there. It's just as valid. Plus, thinking about this stuff is like a mental exercise in visualization, problem solving. And it's good just to keep perspective of our own place in the universe on our gorgeous little home planet. All right, I'd say that this is as profound and abstract as we'll get in this course. After all, I want this course to be applicable and useful to us in our everyday lives. So why talk about theoretical asteroids, playing God like a simulation game, and other planets and stuff? Well, in order to have a deeper understanding of how and why gravity does what it does, I think it's important to know that the very rules that govern our gravity apply everywhere else in the universe too. That's physics, baby. Okay, so to summarize, every object with mass is attracted to every other object with mass. The more massive the two objects are, the greater the gravitational attraction. And the closer the objects are, the greater the gravitational attraction. Some objects are just not very massive or are extremely far away. And in those cases, the gravitational attraction between them can be so small that we essentially consider it to be zero. But when an object with mass is gravitationally attracted to something, say something large, like Earth, we say that that object has weight. Weight is really just the fact that Earth's, or some other large body's, gravity is pulling it down toward its center. The weight of an object can change depending on where it is in the universe in relation to other objects with mass. But the mass of an object can never change. So long as the object is made of all the same stuff, its mass is the same anywhere it goes in the universe. Okay, that's about it for this time. I'll see you in the next one.